Alright, this video is about matplotlib, specifically a submodule of matplotlib called matplotlib.pyplot. Now, matplotlib is a very popular module for plotting, so drawing graphs, so visualizations. And I've put some links to the documentation and to the official tutorial in the version of this notebook, which I'm going to post on Moodle. So we're only going to see a very small part of what matplotlib can do in this video. If you want to know more, you can see their website for that. So this is how we import the bit of matplotlib that we're going to be using. We use import matplotlib.pyplot, and traditionally that's imported as plt, so you can use its functions using plt dot whatever. Let's run this so I've got access to the functions in matplotlib.pyplot. And the simplest plotting command in matplotlib.pyplot is called plt.plot. The simplest way to use plt.plot is just to give it two lists of numbers. So if you give it two lists of numbers, a list of x coordinates and a list of y coordinates, then by default what plt.plot will do is draw a straight line from x1, y1 to x2, y2 to x3, y3 and so on, like this. And they don't actually have to be lists. You can use NumPy arrays instead of lists if you want. So if I call plt.plot with these two lists, then what plt.plot will do is it'll use the first list as the x coordinates and the second list as the y coordinates. So it will draw a line from the point with coordinates 1, 2 to the points with coordinates 2, 1, and then from there to the point with coordinates 3, 2. So let's run it and see what happens. There we go. Ignore the text at the start, which is just telling you something that you don't really need to know. But let's look at the graph that it's produced. So you can see that it's drawn a straight line from the point 1, 2 to the point 2, 1, and from there to the point 3, 2 up here. So it uses the first list as x coordinates and the second list as y coordinates. Alright, now plt.plot is a lot more flexible than this. It doesn't just have to draw straight blue lines between the points that you give it. It can do many different styles of plots. And we'll look at a few of the ways that you can change the plot which plt.plot produces. So for one thing you can do is you can set a title on your plot, you can add labels to the axes, and you can change the style of the line it draws. In fact, you can even stop it drawing a line, and you can just make it draw points at the x and y coordinates that you specify. So let's see how to do this. On line 1, I'm telling plt.plot that I want to do a plot where the x coordinates are 1, 2, and 3. The y coordinates are 3, 1, and 3. And now I've given it another argument, which is a string RO. And what that means is, what I want plt.plot to do is to draw red circles at each of the coordinates that I've given it. So not to join anything up with lines, just draw red circles at the coordinates that I've given it. Okay, on line 2, we're setting a title for the plot. So we do that with plt.title, and we just say what the title should be. Line 3, we specify a label for the y-axis, and we do this with plt.ylabel, and then finally, on line 4, we give a label for the x-axis by doing plt.xlabel. So when I run this, you can see that what I get is now red dots at the coordinates I specified. So a red dot there at coordinate 1, 3, another red dot at coordinate 2, 1, and a third red dot at coordinate 3, 3. That's the function, that's the result of using RO like this. And you can also see the title, which I set on line 2, the y-axis, which I set on line 3, the y-axis label, and the x-axis label that I've set on line 4 there. Alright, so that's how you can label parts of your plots. Let's think about a kind of standard mathematical usage for plotting, which is drawing graphs of functions. Like you've got some function f of x and you want to plot the graph of y equals f of x. We're going to look at how to do that using plt.plot. So the idea will be, we generate a long list of x coordinates, then we generate the corresponding y coordinates. So if your x coordinate is x0, then your y coordinate will be f of x0. And then we'll take those points and we'll just join them all together with straight lines. And assuming f is smooth enough, like differentiable enough, that will be a good approximation to the real graph of y equals f of x. So let's try this. I've got some code here which is going to plot for me the graph of the function sine x. So I want to use Linspace from NumPy to generate my x coordinates. So I'm going to begin on line 1 by importing NumPy as NP. And I also want to graph the sine function. So to get the sine function, I need to import math so that I can use math.sine. Right, now it's really, really easy for us to do what we want to do because we can generate the x coordinates just using Linspace. So remember that Linspace start, stop, n produces n equally spaced points beginning at start and ending at n. So here I've got Linspace 0, 2 pi, 100, which is going to produce 100 equally spaced points between 0 and 2 pi. Then I want my y coordinates. So I want to work out what is sine of each of the x coordinates in my list. And that's really easy to do with a list comprehension. We actually mentioned this before when we first met list comprehensions. So we just do y's, which is going to be the list of y coordinates, is going to be math.sine x for each x in x's, which was our list, or rather array of x coordinates. Okay, we've got our x coordinates, we've got our y coordinates. All we got to do now is call plt.plot with the x coordinates and the y coordinates. When we draw it, we get a nice smooth blue graph of y equals sine x. So it's kind of fun to change that a little bit. I mean, let's see, was 100 points, was that really far too many? And what happens if we do something silly like 5 points? So if you do 5 points, you get this nice spiky version of sine x, where it's not really a very good approximation because we didn't have enough points. But if you only go up to 30, I think you actually still get a pretty nice smooth approximation to y equals sine x. Obviously, you could put something enormously large there and use a very large number of points. But if you do that, it might take a long time to draw your plot because Python has to do a lot of computation to work out 10 million x values and 10 million y values. Okay, we can also have several different plots on the same axis, which might be useful if you want to compare various different graphs. So let's see how to do that, and we'll see a few more customization things that we can do to our plots. So here I am on, oops, let's just get back there. Okay, let's get back to line 1 here. So on line 1, I'm doing the same thing as before. I'm going to make 30 equally spaced points between 0 and 2 pi to use as my x coordinates. And what I'm going to do now is plot the graph of y equals sine x and the graph of y equals cos x on the same axes. So on line 2 here, I'm generating the y coordinates for the graph of sine x, just like before. And on line 3, I'm creating a list called z's, which is going to be the y coordinates for the graph of cos x. So that's exactly like what we did before, except with cos in place of sine. So in order to get two plots on the same axis, all you do is do two plt.plot commands in the same code cell. And if you want to make some kind of visual distinction between the two graphs, so you can see which one is which, then one way you could do that is by specifying how it's going to draw the points on your graph. So here I've used r plus in my graph for sine x, and what that will do is instead of drawing a straight lines between my points, it will draw a red plus sign at each of my x and y coordinates for sine x. Then I've got a new function which is label sine, so a new argument rather, label sine. What that will do is it will be used later to produce a label for the curve which represents sine x. Okay, next we do the same thing for our graph of cos x. So we give it the x coordinates, the y coordinates for the graph of cos x, which was in z's. And then I say g dash dash. The next argument is the string g dash dash, which means Python will use a green dotted line for the graph of cos x. And then finally we have a label for that as well. So this label on its own won't make anything appear, but when I use the legend command later, it will use that label. Alright, so on line 6 we set a title just like before. On line 7 and 8 we label the axes just like before. But on line 9 we do something we haven't seen, which is to do Plt Legend. What that does is it adds a box identifying each line on the plot using the labels that we specified on line 4 and line 5. So it will call the red plus sign line sine, and it will call the green dotted line cos. And finally on line 11 there's again something new. It's going to print grid lines on the plot. Okay, let's run this and see what's happening. Just comment on what's happening. So the legend, so line 9 is this box at the bottom here where it's telling you that the red plus signs are the graph of sine x and the green dashed lines are the graph of cos x. And indeed you can see that the green dotted lines there, which were produced by g dash dash, those things are what made up the graph of cos x, and red plus signs, which is what this r plus produced, is what we got for the graph of sine x. So there we go, two graphs, two plots on the same axis. Now something strange happened in that function call which we've not seen before, which is plt.plot was called with a bunch of arguments written as usual, and then this strange part here which says label equals quotes sine quotes. And we haven't used this kind of function call before. This is what's called a named argument to a Python function. And what it does is it allows you to specify default, so named arguments allow you to specify default values for inputs to your function. That can be useful when your function is very complicated and takes a lot of arguments. So plt.plot, for example, has many different arguments you could specify. I forget how many exactly, but there must be 10 or 15 different arguments you could specify. And if you had to write down all of those, like 15 different arguments every time you called plt.plot, it wouldn't be a very useful function. It would be very painful to use. So what named arguments allow you to do is to give a default sensible value, like plotting a blue straight line, to some of the inputs to your function, which the user of your function can then change if they want to by using this syntax where we specified the name of the argument, which was the label, and then said that the label should be the string sin. So let's see how to do this ourselves. So I'm going to create a function which has some named arguments. So here my function is called f, it's got an argument x which doesn't have a name, and then 3 more arguments, a, whose default value is 1, b, whose default value is 2, and c, whose default value is 3. And it returns just some arithmetic expression involving a, x, b, and c. So when I run this, this is defined, and let me show you now how we could call this function if we wanted. So if I call f of 0, then it will use the default values for a, b, and c because I've not specified them. So it will just work out 1 times 0 plus 2 all divided by 3, which is 2/3. Okay. On the other hand, if we want to specify a value for c, we can do that by just saying f of 0 and then comma and then c equals 1. So that will leave a at its default value and b at its default value, but it will change c into 1. So the computation it will be doing is 1 times 0 plus 2 divided by 1 because c is now 1. So when I run it, I get 2 as expected. On the other hand, you can use the same syntax to change a if you like, and if you change it to 0, you get this. And you're not just restricted to changing only one of the default arguments, of course. So if you wanted to specify b as well, you could do b equals 10, and then you specified 2 of the default arguments, and you'll get 0 this time. Okay, so that's how you can create your own functions with named arguments, and it's a useful thing to do when you've got a complicated function which might have a lot of different inputs. So let's look at our final type of plot, which is a histogram or a bar chart. So if you've got a list of numbers, so some numerical data as a list of numbers, and you have a collection of intervals, which we're going to call bins, then what we do in a histogram is to plot a rectangle above each bin whose height is how many data points lie in that bin. So there are 2 different ways you can specify the bins when you use the function plt.hist, which is matplotlib.pyplot's way of creating histograms. So you can do plt.hist and then your data in a list, and then bins equals n, to say I want to use n equal with bins. On the other hand, you can also specify the intervals manually. So if you do plt.hist and then your data, so the list of the numbers whose histogram you want to plot, and then bins equals a list of numbers like this, b1 up to bn, then the bins it will use are the intervals which are closed at b1 and open at b2, and then the closed interval at b2, the interval which is closed at b2 and open at b3, and so on, and then the final interval will be closed at both ends. Okay, so let's see this in action. I'm going to imagine or simulate rolling a 6-sided die lots of times. So to do that, I'm going to import the random module, which we met before. I'm going to make my die, so the faces of my die are labeled 1, 2, 3, 4, 5, 6. So that's on line 2, I create my list of the faces of the die, 1, 2, 3, 4, 5, 6. Then on line 3, I use a function called random.choices from the random module to take 50 elements, so 50 random elements from faces. So this does a sampling with replacement, which just means it picks one of the elements of faces, and then it picks another element from faces. It could be the same one, it could be a different one. Then it just keeps doing this 50 times and gives you a list of 50 elements. So 50 randomly chosen numbers between 1 and 6. So on running this, I've got the data that I want a histogram of. And I want to draw a histogram which tells me how many 1s I got, how many 2s I got, how many 3s I got, and so on. So the way I'll do this is with plt.hist, and then I'll specify the intervals manually, and I'll do that in such a way that the first interval's got a 1 in it, the second interval will have a 2, the third will have a 3, and so on. So I've chosen my endpoints so that my intervals all have length 1, so the bars will all have the same width, and so that 1 lies in the first interval, 2 lies in the second interval, and so on. So when I run this, I'm going to get my histogram, and I've got 50 rolls of the dice here. So if you see what it's like, I get some rubbish, and I also get these plots which are showing me, look, there's 1, and I can see how many times I got a 1, I can see how many times I got a 2, and so on. And yeah, I seem to not roll 5s very much. That's interesting. Okay, so if you did this a lot more times, for example, let's do this, instead of doing 50 times, let's do 5,000 times, see what happens. If we plot this, okay, it looks a bit more uniform this time. So yeah, that's how you can create your own histograms using matplotlib and plt.hist.